moves over the other. Friction is a necessary evil of engineering life. In any assembly with moving components, both friction and wear will tend to occur wherever two surfaces move against each other. In cutting a material, engineers have to take friction into account. This is what it can do. The drill fails. You can see the effects of friction almost everywhere. On touchdown, clouds of smoke shoot from the tyres of this jumbo jet. It's because of friction between the tyres and the runway. Sometimes we rely on friction. In a chuck, for instance. And it's only friction which holds the taper shank in place. So, if friction is sometimes the enemy of efficiency, it's also a phenomenon we can't do without. This car can't stop because friction between tyre and road has been reduced by a film of water. This simple experiment helps us to understand more about friction. A surface plate looks perfectly smooth and flat, but when we try to push it across a steel bench top, we encounter some resistance. We get a kind of stick-slip motion. If we could look at these two smooth surfaces under a microscope, we'd see something like this, a series of peaks and valleys. The peaks rub against each other as one surface moves over the other. We can separate these peaks by putting a thin film of oil between the two surfaces. And of course, the motion becomes easier. So, one way you can reduce friction is by using a lubricant. You can make the motion even easier by putting rollers between the surfaces. Now it's much easier to move the surface plate over the bench. Though without friction, the rollers would slide instead of turning. It's even easier if we use ball bearings. Now we can move the plate around over the workbench with very little resistance. Though once again, remember, it's friction that makes the ball bearings roll instead of slipping. Does friction depend on the types of material in contact? This cube has 4 different faces. Let's put a plastics material in contact with a mild steel surface. It takes very little force to move the cube because it's a low friction material called PTFE. What about mild steel? More weight means more friction. Now brass. Even more friction. And lastly, copper. So friction depends on the types of material in contact. Whenever you try to move one surface over another, the force of friction will resist the motion. You have to apply enough effort to overcome that resistance. Obviously, you need more effort to shift a bigger load. But that's because the friction also increases if you apply any kind of downward force to the two surfaces. The bigger the load you apply, the larger the friction. And the more effort you need to overcome the resistance. Engineers make use of this basic principle all the time. For example, in work holding. By applying a large downward force to a clamp, you increase the friction between the work and the slideway, making it more difficult for the work to slip during cutting. The design of a car brake relies entirely upon friction. Early cars, like this 1919 Wolseley, used a simple shoe brake design. When you applied the brake, a high friction material was forced against the wheel to bring it to a halt. Modern designs are rather more complex, but the principle is basically the same. The disc brake unit is mounted against the hub of the front wheel, with two pads of a high friction material inserted on either side of the disc. You can see the design more clearly on a diagram. When you apply the brakes, this high friction material is squeezed against the disc to stop both disc and wheel rotating. The harder the pads pinch the disc, the greater the friction. And this depends on how hard the driver presses the pedal. In this car, the force applied is measured on a dial. 400 units. This time, the driver will brake twice as hard. More force, more friction. Disengaging a clutch separates it from the engine flywheel, so that the wheels are no longer driven. The clutch engages on the flywheel by means of high friction material on the back of the cone and transfers the drive from the engine to the prop shaft. A drive belt also relies on friction. Friction belts are used in a wide range of engineering situations to transfer power. When this belt is slack, the pulley on the left remains stationary. Adjust the tension and the drive is taken up because of friction between the pulleys and the belt. In work holding, it's again important to increase friction. You can do this by increasing the load on the work. With a surface grinder, you do this by using a magnetic force, as this demonstration shows. To show what happens without the magnetic force, we took the guard off and turned the wheel slowly by hand. Something you must never do. Though friction is sometimes useful, it's often a nuisance, causing wear and inefficiency. For example, a car engine would seize up without oil. Machine tools are highly complex assemblies containing many moving and rotating components. To avoid wear on the slideways, friction must be kept to a minimum. All machine tools are designed with highly complex lubrication systems. Good design and lubrication of bearings is a fundamental contribution to the efficient running of any machine. This model steam engine has one of the commonest types of bearing, a journal bearing. It separates the drive shaft and the conrod. It's made of phosphor bronze, which is a softer material than steel, and it reduces wear and tear on both the drive shaft and the conrod. In this gearbox, the drive shaft has to take an enormous load, which means there's a lot of friction. Once again, a journal bearing is used. The sleeve contains a phosphor bronze lining, which is softer than the steel drive shaft. As these marks show, the lining tends to wear out first. In machine tools, good bearing design is of fundamental importance. This model shows the mechanism of a shaper. The up and down movement of the central bearing determines the length of strike. We overrode the safety lock on a shaper to show you the bearing in action. It's made of cast iron, moving on steel runners. Friction between these two materials is fairly low, and this factor, combined with good lubrication, keeps friction to a minimum. It's easier to move something on ball bearings than to slide it. By separating the components in a cage, friction between them is reduced. This exploded model of a car engine shows the ball bearings in the differential, and you could find many more examples. Roller bearings are more effective for heavy loads. This one is on a test rig in a laboratory. Load is applied at the top of the bearing by a hydraulic system. Because of the load, friction will be greatest at the top and bottom of the bearing. At the sides, there is very little friction, and the rollers tend to slip wherever friction is reduced. This is a rig for testing disc brakes. We're going to use it to show you one effect of friction. Apply the brakes at 1500 revs. The temperature of the disc is beginning to rise. That's because of friction. Repeated applications of the brake raise the temperature more and more. Eventually, the brake pads get so hot they catch fire. In some cutting operations, you can see the same effect. This lathe was specially set up to show what can happen if you cut dry. The excessive heat has completely destroyed the tooltip. Cutting dry can have another effect, as you can see in this high-speed film. Friction causes material to build up on the face of the cutting tool, changing the rake angle and shortening the life of the tool. And here's something you may have done yourself. Turning against a dead center and using no grease. Friction between the rapidly spinning work and the dead centre has generated so much heat that the tip has actually welded to the work. We repeated the entire cutting operation, putting grease between the centre and the work. And this time we also used a coolant. Quite a dramatic change. Coolants and cutting fluids are used to conduct away the heat which friction tends to generate. They also protect the tool tip and the surface finish of the work. But sometimes the heating effect of friction can be used to advantage, in friction welding, for example. The join is completely invisible. This specimen bar shows a number of different metals which have been joined together by friction welding. Another effect of friction is wear. You can see the wear marks on the teeth of these gear wheels. And here's another scar on a machine tool slideway. This can spoil the rigidity of the machine. This rig shows how wear on moving surfaces is affected by load. The scar is simply due to the weight of the rig, but now if we increase the load, the scar is deepened. This situation looks pretty similar. But can you think why this hard stylus doesn't wear a groove in the soft material of the disc? On this milling machine, we've set up a meter to measure the power consumed during the cutting operation. As the cutter clears the work, the power consumption drops. Now it's no longer cutting, but it's still using up a lot of power. And here's the reason. Power is used up in overcoming the friction between all the gear wheels which drive the cutter. That's why we call friction the enemy of efficiency. Heat, wear and power loss are three effects of friction which engineers must always take into account for the efficient running of any machine.